So this will be the first lecture on AC circuits. There will be a second lecture posted later. In this particular lecture, we're going to go over the following points. We're going to talk about AC sources in general, and then focus a little bit more on this new concept called phasors. And then we're going to see how resistors and capacitors are included in an AC circuit. There's also a new concept, capacitive reactance, that will be introduced, and then we'll bring them together into RC circuits to see how this works. So with AC circuits, the new thing is that the source of voltage, the EMF, is no longer constant, and in this case it will be an oscillating function. We talked about different possibilities for an AC circuit, but for this lecture I'm going to focus exclusively on sinusoidal functions, and more specifically, to follow the textbook, I'm going to use the cosine function. So in this picture you can see the EMF starting at a peak value of E0, and then over time is oscillating back and forth with a period called capital T. That would be the time it takes for the oscillation to repeat itself. And then we tie this with the angular frequency omega, which is right here, which is itself connected to the regular frequency. So the regular frequency is in hertz. Omega is in radians per seconds. That's the difference between angular frequency and frequency. So the EMF is now going to be represented by this function. E naught represents the peak value or the amplitude of the signal, and then omega is the angular frequency, and this is how we will write down the function for the EMF. Now, we need to use a different technique for this chapter to represent the function, especially for combinations that will come up later with RC and especially RLC circuits. So a phasor is a technique that allows us to show quantities that are oscillating in a vector form. So just to go back to the example from before, when we see the EMF at any given time as E naught cosine omega t, you can think of it as the projection on the horizontal axis of a vector of magnitude or length E naught, and making an angle with respect to the horizontal axis omega t. So when you project this at a given time, you take in the projection on the horizontal axis, that would be whatever the length of the vector is, that's E naught, multiplied by the cosine of the angle, which happens to be omega t at this point. Now the vector is going to keep moving. It's a rotating vector. That's what the phasors are representing. But at any time we are interested in the projection on the horizontal axis, and then we'll also keep an eye on the magnitude. That doesn't change. The E naught is the amplitude of the signal. It's the maximum value, and it will not change, but the angle itself will change. It goes around. By convention, we are using the counterclockwise direction as positive. So in every question or every diagram, it's always going to be the case. All right, so then if we look at the EMF changing over one period, let's say, and we look at the phasor corresponding to the value of the EMF. So at time 0, the EMF is at its peak value, E naught, and so the phasor, remember this is it's a projection on the horizontal axis, so it's E naught times cosine omega t. So the omega t is 0 at this time, and so E naught cosine omega t will be the maximum value, which will be E naught. If you wait a quarter of a period later, here, now the omega t will be equal to pi over 2. If you go back to the definition of omega, you'll see why. But then the cosine of pi over 2 is 0, and therefore the EMF is going to be 0 at this stage. And so this is what we see here. The EMF is crossing the 0 axis. Another quarter period later, and now the omega t product is pi. The cosine of that is -1, and therefore the EMF is negative E naught. And you can see here that the vector representing the EMF, the phasor, is going to be on the horizontal but pointing to the left, whereas here the phasor was pointing straight up, and here the phasor was horizontal and to the right. We keep going, and 3/4 of a period later, The phasor is going to be pointing all the way down because the omega t product is now 3 pi over 2, which brings the EMF back to 0. So it's 0 here, it's 0 here, and it's at a minimum here, negative E0 here, and maximum over here. So again, the phasors are going to point down here and to the right on this side. Okay, so here's a quick question related to this. So this is representing a current phasor. We haven't said what that is yet, but essentially it's another vector that will be rotating counterclockwise as always. And we are looking for the instantaneous value, that is at a given time. What does the value of the current do at this particular point? Is it increasing, decreasing, is it constant, or you can't tell without knowing which way it's rotating. So you should pause here for a second and think about the question. And I'm going to assume that you did that, and here's the answer to this question. So the answer is that it's increasing because by convention we said that the vectors or the phasors would always be going counterclockwise. So if we see it at this instant, it's going to be going later to something that may look like this, if I can represent a vector like this. And so the projection on the horizontal axis is actually going to increase, and that's why we are in a phase where this is increasing. As the vector rotates to counterclockwise, its projection on the horizontal axis will be increasing. All right, so now we are going to include elements or components in our circuit connected to the EMF. For resistors, we'll be interested in the voltage across the resistor and as well as the current going through the resistor. We're going to change notation slightly. Instead of capital I, we're now using lowercase I. In this case, we put a subscript for the current, for the current being in the resistor, so we put an R. The voltage is measuring the potential difference across the resistor. That keeps changing with the AC voltage, but we know it's always going to be connected to the current through this relationship: voltage equals current times resistance. Okay, so in the circuit, here's what it looks like. We have a source of EMF right here. That will be a cosine function. At the same time, there's a current running through the circuit, and we are interested in the voltage across the resistor. And so Ohm's law is still applicable here. And so we would look at the current as being the ratio of voltage over resistance. Given that the voltage is now a function of time, the current also ends up being a function of time, as you can see here. So in this notation, we use IR for the peak value of the current through the resistor, and the peak value is going to be the ratio of VR over R, and that is very similar to what we did in DC circuits. All right, so a quick question, quick representation of the voltage and the current at the same time. So they're put on the same graph. Technically, we remember that these are not the same units, so they don't really compare to each other, but at least the pattern over time is similar. So here we have the voltage across the resistor, so we know it's a cosine function, and the current across the resistor, which is voltage over resistance, that also is a cosine function. So the two functions behave together. That is, they get to zero together, they get to the minimum together, and again to the peaks together. And so when we represent this with phasors, we will have here two phasors, one for the current and one for the voltage. Remember, the phasors are just generic vectors that are rotating, and they're rotating counterclockwise. And so we pick up a particular time here, omega t, and at any given time, the voltage and the current would both be in phase. That is, they'll be reaching the peak and the minimum together. And when we project them on a horizontal axis, we will get the instantaneous value of the current or the instantaneous value of the voltage. These two are still connected by their Ohm's law. That is, VR is IR multiplied by the resistance. But we are looking here at the phasors, and so we're looking at the vectors representing the V and the I. Okay, now in the case of capacitors, we know capacitors are charging, and whenever they're charging, there's going to be a voltage across the capacitors. But in the case of AC voltage, the current is going to keep changing direction back and forth, and so the capacitors will be charging and discharging every time the current changes direction. Then there is a reversal of what's going on through the capacitor, but that doesn't change the fact that the voltage across the capacitor is still equal to whatever the charge is on the capacitor divided by its capacitance. So in the circuit where we would have maybe just a EMF with this cosine function connected to a capacitor. So for this particular circuit, we assume the capacitor is the only thing connected. So here we've got the charge at any given time on the capacitor is going to be the capacitance times the voltage across the capacitor. And in this case, the voltage across the capacitor is going to be, because there's nothing else connected here, is going to be, again, a sort of cosine function connected to the voltage across the capacitor, across the EMF, because remember, since the capacitor is the only thing connected to the EMF, they will have the same voltage. But if we're interested in the current, remember that current is defined as the derivative of charge with respect to time. So when you differentiate this, you're actually going to get something that looks a little different. Because of the cosine function, we get first a negative sign, and then we get a sign instead of a cosine right here. Well, to be able to compare things, we're going to use a trig identity. And this particular trig identity, you can look it up later, is such that the negative of a sine of an angle is the same thing as a cosine of that angle plus pi over 2. So that allows us to pick up this expression here and rewrite this as a cosine function by adding a pi over 2 here. And then there will be a term in the front that will be eventually referred to as a maximum value of the current, but that's for later. So when we represent this as a function of time, now here's a voltage, again, peaking at 0 because of the choice of cosine function, and then it oscillates as usual. But if you look at the current, which is cosine of omega t plus pi over 2, so we have to add pi over 2 every time, and that leads to a pattern that looks like this. It's not in phase with the voltage anymore. So there is a difference between these two. And when we get to the phasor representation, well, here's the phasor for the voltage at any given time. So this is it. And we have the omega t right here. But the current, if you remember from the previous slide right here, the current has an extra pi over 2 in its equation. So when we add this here, we will have to increase the angle with respect to omega t. We have to add another pi over 2, and that gives us this angle. And so, again, the instantaneous value of this vector here is going to be somewhere on the horizontal axis. But the important thing here is that the current and the voltage are no longer in sync. And in this particular case, for the capacitor, the current is ahead of the voltage. All right, so here's another question for you. And on this question, it says that we have two phasors that represent some kind of circuit. And the question is, what's the current doing with respect to the voltage? Is it leading? Is it lagging? Is it perpendicular to? Or is it out of phase? Okay, so same deal as before. Pause here for a few seconds. See if you can answer the question on your own before I show you the answer. So the answer is that the current is lagging because, as you can see from the picture, the current is trailing the voltage. That is, the angle, whatever the angle is on the voltage, the angle for the current is behind. We wouldn't say that the current is perpendicular because that doesn't really mean much. I mean, vectorially, yes, you can see the two vectors are perpendicular to each other, but that's just a representation. It doesn't mean that the current is perpendicular to the voltage. So here's another question, which is about the graph of voltage versus current. And so what can you say about this one here? Okay, so is the current lagging, leading, less than, or out of phase with the voltage? So take a second and see what you can say. All right, so the answer here is that the current is lagging the voltage. One more time. Here, the voltage is already at a peak, whereas the current is going to get to that peak a little later. Okay, so technically here you could say that it's out of phase with the voltage, but I guess for this particular question, the better answer was that the current was lagging, which is really what we are interested in at this point. Okay, so notice that there was a peak value for the current across the capacitor, and that combination of term will be referred to as the peak current. So omega C times the voltage across the capacitor, that defines the peak current. Well, in order to compare this or write it down in a very similar way to Ohm's law, we're going to define something called a capacitor reactance. And sorry, there's misspelled here. Should be an I instead of an A, but this is the proper spelling of the word, capacitive reactance. So this is defined as 1 over omega C. And when you use this particular combination of terms, omega C and 1 over omega C, then you can write down the current, the peak current, as V sub C over XC. And this makes it look very much like Ohm's law. So we can think of the capacitive reactance, this quantity here, as something like a resistance. And we can then structure the equation just like what we had V equals IR for a resistor. Now we have the reactance for a capacitor. So the capacitor may look like it's behaving like a resistor, except that the behavior is dependent on the frequency of the current. So depending on how much omega is, we will get a different capacitive reactance. And so this graph shows you the function. So if you look carefully at this, as omega increases, the capacitive reactance is decreasing. And this will have an impact, as we will see in a few minutes, on the behavior of a circuit, especially circuits that include a resistor. And that's what makes AC circuits a little more interesting, because there are some behaviors that are associated with time. All right, so here's another question for you. I should probably clean up a little bit this. Let me see, we should take this off. Okay, so let's grab this again. I'm not sure why I'm getting these things here, but anyway, so the question is, so if the value of the capacitance is doubled in the circuit, what would happen to the capacitor reactance? Would it be quartered, half, doubled, or quadrupled? So think about that for a second, and here's the answer. It is half, because the capacitor reactance is 1 over omega C, so if you double C, then this will be decreased by a factor of 2. Okay. Another question, so what if we double the capacitance? What happens to the peak current? Okay, again, same options. And if you pause for a second and go on and work out the question, here's what you should come up with. Then the current is doubled, because the voltage across the capacitor, that's not changing in this particular case. It is just VC, same as the EMF of the source at this point. But if we double the capacitance, and remember the capacitor reactance was halved, so that would actually double the current in the circuit or through the capacitor. A quick example here with calculations. So here's a case where you have a capacitor of 0.1 microfarad, and the question is to find the capacitor reactance at a frequency of 100 hertz. And so what you need to do is calculate 1 over omega C for this. You have to remember that omega is 2 pi times the frequency, so you have to multiply 2 pi by the 100 hertz. You put in the capacitance, and you end up with 16,000. Notice here the units are ohms, which is what's interesting about the capacitor reactance. There will be something similar for the inductors later. They are in units of ohms, and so they are very similar to resistors, except that, again, if you change the frequency, the omega, and then this number will change as well. So here's another question. What is the current through a capacitor at this point when you have 1,000 hertz oscillator, and that is the frequency of the signal is 1,000 hertz. You have 10 microfarad for the capacitance, and the peak EMF is 5 volts. The question is, what's the peak current for the capacitor? So to get this answer, we need to combine a few things. So first we figure out the capacitor reactance, omega being equal to 6,280 radians per second. We put it in here and we end up with a capacitor reactance of 16 ohms. Now the peak voltage is going to be whatever the peak current is going to be the peak voltage over the capacitor reactance, so 5 over 16. That should be 0.31 amps. Okay, so now let's put this together with a resistor. So in this particular circuit, we have an AC source with a resistor and a capacitor. They're in series. So one thing that connects them together is they will have the same current because they're in series. And so we're going to look at the behavior of the circuit. One of the important things is that the frequency will make a difference. And so depending on whether the frequency is low or high, some of these voltages will have different values, and we will see some of the special cases in a moment. So one of the things we want to do is find the relationship between the current and the voltage for each of these elements, the resistor and the capacitor, but also with the EMF, the E naught. So let's go to the phasors, and this will take a few steps. So we want to see what the current is going to look like when compared to the voltage. So we begin by imagining a phasor. It doesn't matter what the angle is here. We'll adjust that in a moment. We will call this the peak, the maximum current is I. And we'll start with the current because all of these elements, the resistor and the capacitor, are in series, so they have the same current. So what we know is that if this is what the current looks like, the voltage across the resistor is simply current times resistance, and it's going to be therefore a vector, maybe a different length, just to differentiate them. Remember, these are different units, so comparing them is not really that meaningful. But the voltage and the current are in phase when it's a resistor, so the phases will also be in phase. For the capacitor, remember the current was leading the voltage, and leading by an angle that turned out to be pi over 2. So if this is a current, the voltage across the capacitor will be behind it at a 90-degree angle, or pi over 2. All right, so then when we combine these two, so this is a voltage across the resistor, this is a voltage across the capacitor. When we combine these two, we add the vectors, and this is where the phasor technique becomes really useful. So we know how to add vectors. We take these two vectors, the VR and the VC, and we combine them as vectors, so we end up with this vector. This is the EMF of the source, because remember that the two voltages for the resistor and the capacitor add up to the voltage of the EMF, and this is where the omega t comes in. So this vector, this is the voltage of the source, is going to make an angle omega t with respect to the time axis. And then we want to get the magnitude of this vector in terms of the VR and the VC. So, as always, for a triangle, a right triangle, the length of the hypotenuse, which is what this E naught represents, is going to be E naught squared is going to be VR squared plus VC squared. And so now this is getting us the peak value. If you want to get the currents, remember that the peak value for VR is peak current multiplied by resistance, and then for the capacitor, peak current times reactive capacitance, capacitor reactance rather, is giving us the voltage, the peak voltage across the capacitor. So now we bring this together, we combine the pieces here, and we end up with a relationship between the EMF of the source and the components of the circuit, that is R and C. They get put together this way. And now we can solve for the peak current in terms of the EMF of the source. And notice that now the relationship is a bit complicated, but we get this current from this equation right here. So if you solve this equation for I, you'll get E naught over the square root of R squared plus XC squared. And then, now that you know the current, if you want to know the voltage across, say, the resistor, you'll multiply voltage by, the current by resistance, and you get this. So here's the expression of the current. You multiply by the resistance, and you get this. For the capacitor, we have the relationship with the capacitor reactance. So we multiply the current by the capacitor reactance. And if we insert the capacitor reactance as 1 over omega C, this is what we get. Now, what's interesting about this is that there is a pattern here. Remember, the voltage across a resistor and across a capacitor behave in a different way. So this is what we get when we combine the two quantities. If you look again at this combination for VR and VC, you'll see that as the frequency increases, if we measure the voltage across the capacitor, it's going to decrease and eventually become so small that we can ignore it, whereas the voltage across the resistor, as we increase the frequency, that's increasing all the time until we get to the maximum it can be, which is the EMF of the source at infinite frequency. And there's this thing called a crossover frequency, which happens to be 1 over RC. Very similar to what we have seen earlier when we talked about the RC circuit, that was connected to the time constant. So this is actually 1 over the time constant. All right, so in this circuit, is it true that the peak voltage VR plus the peak voltage capacitor is equal to the peak voltage E naught? Yes, no, or you can't tell without knowing omega. So think about that for a second. And the correct answer turns out to be no, because what we are combining here are the peak voltages. And remember, we had to do some kind of Pythagorean theorem to figure out the relationship between the VR and the VC. They don't just simply add up like this. What do add up are the instantaneous values, the instantaneous value of the voltage plus the instantaneous value of the capacitor, or the voltage across the capacitor. That's equal to the instantaneous value of the EMF E here. But the peak values do not add up like this. So here's where things kind of get interesting. So suppose you have an RC circuit hooked up like this, and you measure or you pick up the voltage across the capacitor. And so what you'll measure across here, the output of your circuit, will be the voltage across the capacitor. Now, if you have a varying frequency, if you change the frequency of the signal here, well, you remember that the voltage across the capacitor is actually going to decrease with the frequency. And if you have a high frequency signal, then the voltage across the capacitor will be basically 0. If you go back a couple of slides here, this was the voltage across the capacitor. So this is the behavior of the voltage across the capacitor. And so here, the voltage across this capacitor will decrease. And so at high voltage, at high frequency rather, there won't be any voltage left here. And so you can say that the capacitor or this circuit is blocking any high frequency, and so it's referred to as a low-pass filter. It allows low frequencies to pass, but it blocks higher frequencies. The opposite would be a high-pass filter. So it's basically the same circuit. You notice here it's R and C, but we're picking up the voltage across the resistor, and when we do that, the voltage across the resistor, remember, is going to be increasing as the frequency is increasing. And so when we have a high pass filter, the voltage here is going to be you'll have a higher voltage when the frequencies are high. When the frequencies is low, you're not going to get much of a voltage here. So this will be referred to as a high-pass filter. It allows high frequencies to go through, but it will block the lower frequencies. So this is where the RC circuit in an AC with an AC source become interesting, and you can use them to filter frequencies, and that has a lot of interesting applications. So this is it for this lecture. Next time, I'm going to talk about inductors, inductive reactance, very similar to the one for a capacitor, and of course combine that with resistors, RL circuit, and then we'll get to the really interesting thing about AC circuit when we have a resistor, an inductor, and a capacitor. And then there will be a discussion of power in the context of AC circuit. So now that you've watched this video, the next step is to go to Canvas and answer a short quiz connected to all the items discussed in this video, and this will be it for this particular assignment.